Ladies and gentlemen, thank you for joining us on this special occasion. Tonight's topic is balls. But don't get too excited. Just the balls in ballpoint pens, presented by Preet Shah, Ahmed Ibrahim, and Ryan Smeets.
So I'm sure everyone knows what a ballpoint pen is, but for the sake of this video, I'll explain what it is. It writes stuff. Now to the important things. For the average person to be able to purchase one so cheaply, a lot of thought and careful design goes into the manufacturing and material selection of the pens. More specifically, the ball in the ballpoint pen has to be made of a material that's hard enough, strong enough, and smooth enough. An extremely small reduction in the mass of metal used can lead to enormous cost savings, as well as a significant reduction of wasted material. So what we would ideally want is a material that has the perfect combination of mechanical and thermal properties in order to maximize performance and reduce costs. Taking a closer look at how the ball is actually made, we can see that it is manufactured quite similarly to the balls and ball bearings. Basically, the metal used is drawn into a wire or deep drawn into a sheet in some occasions, which is then cut into smaller pieces. It is then forged and extruded in a die, and then is deflashed and grinded to remove excess material. Finally, the ball is heat treated to reach the required hardness. In current production, the material used is tungsten carbide, which has a combination of desired strength, hardness, and corrosion resistance. You may be an engineer at Waterloo, but do you really know how a pen works? It's actually really simple. Behind the ball is a tube that acts as a reservoir that stores ink. Due to gravity, the ink flows down and around the ball, and is then transferred onto the paper below it. This is because the paper's surface area is larger than the ball's, due to it being more fibrous and thus more sticky to the ink. Thus, it grips onto the ink more and is transferred onto the paper. The main objective of this material selection process is to reduce the costs associated with the production of the balls, which in turn leads to increased output. We came up with 4 functional requirements for this material selection. The first is that the ball must withstand an average force of 8 newtons, which according to our approximations is the average force you exert on the pen while writing. The force it must withstand increases to 16 newtons with our factor of safety of 2. The second requirement is that the material should only expand so much for a certain change in temperature. The material should also have sufficient resistance to corrosion caused by the ink, which is usually water-based. The last requirement is that the ball must have a minimum hardness of 80 HV to prevent abrasions and scratches. Our 3 variables in this material selection were the radius of the ball and the choice of material.
Now we're going to be talking about our MPI derivations for our first functional requirement. Beware, this might be extremely boring. Our first functional requirement was a minimum applied load of 16 newtons. This includes a factor of safety of 2. The formula we used was yield strength is equal to force over area, and since the ball is a sphere, the cross-sectional area is pi r squared. Our objective is to minimize costs, and so our cost function was mass times price, and mass can be represented as volume times density. Volume then can be replaced for 4 pi r cubed over 3. From here, we isolate for the free variable radius in our first equation to get square root of force over pi times yield strength. We substitute this function into our cost function to get that equation you see right there. From here, we're going to assume a cost of 0.001 cents or 0.001 times 10 to the negative $2. Now, you can say Q is equal to yield strength to the power of 3 over 2 divided by density times price. Cost can equal K over Q, and from here, Q can equal K over cost. Substituting the values in for force and cost that we came up with before into K and cost, you can get a Q value which is equal to that value right there. From here, we can take log of both sides of the Q function to get the equation you see at the bottom of the screen. And from this equation, you can see that slope is equal to 2 over 3, and a point on the graph, taking density times price equal to 1, gives you the point right there. From the previous slide, we can use the slope and a point to graph out the line you can see here on a graph displaying Young's modulus versus price times density of different materials. All the colorful little dots you see are all the materials that pass our initial test of a minimum load of 16 newtons being applied to them. Next is our MPI derivation for our second functional requirement, which was a maximum radial expansion due to a change in temperature. We assumed a maximum radial expansion of 0.0005 millimeters and a change in temperature of 40 degrees Celsius. From additional research, we found that the coefficient of thermal expansion, alpha, is equal to 1 over volume times the change in volume divided by the change in temperature. Volume we know is equal to 4 pi r cubed over 3, and then doing some calculus and derivatives, you can see that change in volume over change in temperature is equal to 4 times pi r squared dr over dt. Substituting this, you can get a final equation of alpha equal to 3 times delta r over r times delta t, where r is radius. So now again, we isolate for the free variable radius to get r is equal to 3 times delta r over alpha times delta t. We substitute this equation into our cost function to get cost is equal to that right there. Again, we're going to assume a cost of 0.001 cents. Now we can say Q is equal to alpha cubed over density times price. And from before, we know that Q is equal to K divided by cost. And if you substitute in delta R as 0.0005 millimeters and delta T as 40 degrees Celsius, you can get a Q value, which is your MPI value of this really small number you see right there. Continuing from our previous MPI derivation, you take the log of both sides, and doing some simple algebra, you get a final equation, which you can see right there. From that equation, we know that the slope is 1/3, and substituting price times density as 1, you can get a point on the graph as 1, comma, that value right there. From our previous slide and the equation we determined there, we can graph the line shown here on a graph showing thermal expansion coefficient versus price times density of different materials. All the colored materials here you see show that they have a maximum expansion of 0.0005 millimeters with a temperature change of 40 degrees Celsius. Our next functional requirement was having a minimum hardness value, which we determined to be 80 Vickers, and this graph here shows all the materials which have a minimum hardness value of that. Our fourth functional requirement was having a material which can resist corrosion in the water-based ink, and this table here shows the number of material that fit in the excellent section of being resistant to corrosion in water. Our final functional requirement had to do with the manufacturing process and picking a material or metal that had a high ability to be deep drawn, so it makes the manufacturing process easier. This table shows that in the end we have a list of 28 metals which have an excellent ability to be deep drawn. From our 5 functional requirements and MPI derivations, we get a final list of 28 materials that suit the constraints we supplied the program. The list shown here is ranked in increasing price times density.
Finally, we've reached the actual material selection portion of the project. From the previous slide, you can see that the top choices were all stainless steel. While these are the options with the lowest price density values, they also have the sum of the lowest yield strengths. This shouldn't be a problem based on the other calculations and assumptions made in this video, but it is something to take into consideration. The materials from the list that have the highest yield strengths are a titanium-palladium alloy and 2 bronze alloys. While these are the strongest, they are also the most expensive. This is why we have chosen to go with the stainless steel option. This was actually a very popular option prior to the tungsten carbide option that they use today. Some of the problems with our conclusions may come from our MPI diagrams. It is hard to come up with all of them, and it's probably why tungsten carbide was never an option for us. Another thing, we made a lot of assumptions. Some of them, maybe even all of them honestly, could have been wrong. Wear and fatigue were also never taken into account. Some materials wear faster than others. Lastly, adhesion was never considered. We're not entirely sure which materials will grip to the ink and to the paper.